right? So in the undergrad level, we learned about deterministic signals, about which we know the properties, right? The properties of deterministic signals we know. So these are known, right? However, in the real world, when we are working with the real world signals, most of the real world signals are random signals, right? Most of the real world signals are random signals, right? So most of the real world signals are random signals, and therefore, in order for us to process the signals that we receive from different sensors, uh, mainly actually sensors, uh, in order to process the signals that we receive through the sensors, we need to understand how to process these random signals, right? So in our signal processing module, in this module, we'll be basically learning how to process uh, the random signals. So signal processing is used to process basically the random signals, and we will be understanding the properties of random signals, and we'll be understanding how to mathematically represent random signals. So when we are doing that, we'll be focusing on many things, right? We'll be focusing on many things, and we will be focusing on mathematical modeling of random signals, mathematical modeling signals, and mathematical. We will be mathematically modeling the signal, and we'll be using uh, concepts related to statistics, basically. Concepts related to statistics will be highly used in order to analyze these random signals, right? So if you talk about statistics, there are many concepts related to statistics. So we'll be talking about like concepts such as mean, mean, variance, other high order statistics, um, about which we will get into in today's class, right? So we are actually talking about all those statistics in this module. Apart from that, we will be using these statistics to filter out the necessary signal components from random signals. So I hope it is slightly bit um, clear to you. However, like we will discuss about these things further. So we also have other like statistics that we will be talking about, which are extremely important not only in signal processing but also in other areas such as machine learning, which you will need to use since it is also a very, I mean, machine learning is a very trending field. So when we talk about the statistics, we can also get other statistics like, you know, likelihood estimation, likelihood estimation, likelihood estimation, and we can take linear regression, linear regression. Likewise, we can take. So we will be discussing about all these, and we also will be talking about filtering, filtering signals, and then we'll be talking about extracting the components from these signals, and analyzing specific parts of the signals. So we will discuss about those in detail. in the next sections of the lecture. So that will be the kind of brief explanation about the random signals and how we will be processing those random signals. So I will start with some questions. So basically, we discussed about random variables and what random variables are in the last class. So what are random variables? What are random variables? Right? What are random variables? So we discussed about random variables having basically 4 features, 4 elements. And we discussed that these 4 elements are basically that random variables should be generated from a random uh, experiment, right? Some kind of a random process, right? Random variables are generated from a random experiment, and the outcomes of those random processes can be modeled or mapped to a real axis. The outcomes can be mapped to a real axis. Okay, so a um, random process has certain outcomes, and those outcomes can be mapped to a real axis. The outcomes that we can obtain from this process or the experiment, we can put them all into a set, and that set we call as a sample space. So we can define a sample space for the random experiment, right? And that sample space we should be able to define a sample space for the random variable. So we need to know each and every outcome of that experiment, and then we should be able to define it in the sample space. And we also need to define the probability of each outcome. We need to be able to define the probability of each outcome, right? So these things I discussed in the last class. So the LJMU students, if possible, please, refer the last week class, and then you can also gain, some more information about these, these ideas that I'm discussing, so that you can, refresh that knowledge. So we discussed about uh, different types of random variables. So there are basically 3 types of random variables. So one is the continuous random variable, and then the discrete random variable, and thirdly, mixed random variable, right? So continuous random variable has uncountable outcomes, right? The outcomes from this experiment is uncountable. So we can define the sample space, but there are uncountable outcomes from that in that sample space. The reason is that between two integers, you can define infinite amount of outcomes, right? So if we take if we take that there's a certain experiment, a random experiment, right? So that random experiment, let's say, has outcomes, right? Outcomes that are mapped to a real axis, right? So if the outcomes from that random experiment can be mapped to -1 and 1, And if the random variable is a continuous random variable, then all the intermediate locations of this between this range also will be outcomes of that experiment. So since there are infinite number of outcomes inside this region, we cannot count the number of outcomes. So because of that, we say that for continuous random variables, the number of outcomes are infinite or uncountable, right? Then we have countable outcomes for discrete random variables. For discrete random variables, we have countable outcomes. So we can count the number of outcomes for the discrete random variables. So we will take like, for example, an experiment where we have discrete random variable, right? So one of the examples is like tossing a die or tossing a coin. So, right, when we toss a coin, we can consider that the outcomes of that coin tossing is a random variable, which is discrete in nature, and the outcomes will be having the heads or having the tails, right? So one of the outcomes will be having the heads or having the tail. So we can define the having the head as 1. We can define having tails as 0, let's say. And then by defining those real numbers, real values, we can say for 0 and 1, what is the probability of getting that outcome. So anyway, like the real values that we define for the outcomes are countable. Like there are 2 outcomes. So the countable outcomes
It
are
can be
there.
more, right?
Yeah, it can be more. I mean, there
And
could be more.
the outcome should be a constant, or the quantity of outcomes.
The quantity of outcomes are countable. Like you can count it.
Count it, and is it fixed
Finite.
value, right?
Fixed value means like it depends on the physical experiment
Okay.
you are taking, right? So defining, if you define different, I mean, ways of doing, I mean, different, I mean, if you define a different experiment, the outcome in that experiment will be different. Means like if you are defining, okay, the experiment of having 2 heads at the same time, right? In that case, the outcomes will be different. You can have different combinations of outcomes. You can have 2 heads, and you can have 1 head and tail. You can have 2 tails, right? Likewise, tail and head. Likewise, you can get different outcomes depending on the experiment you define. So therefore you need to consider the experiment, and based on that experiment, the outcomes and the number of outcomes will be defined. So apart from that, we have this continuous and discrete random variables together in the mixed random variable, right? So in mixed random variable, you can have both, like continuous random variables as output and discrete random variables as outputs of that experiment. So that experiment, what you define, has to be in that nature that produces both these type of random variables, right? If you define a random experiment that measures that combines 2 experiments, such that you define one experiment that generates a discrete random variable, and then you define another experiment that generates a continuous random variable, then the output of these 2 experiments will give a mixed random variable, right? So that is how mixed random variables are generated. Okay, so you will have both continuous outcomes or uncountable outcomes and countable outcomes under mixed random variables, right? So anyway, like we will discuss mainly about continuous random variables and discrete random variables. Using those properties, we can define the behavior of the mixed random variable. So yeah, so I hope it is okay.
Madam, all the time we have to check for the mixed value random variable. All the time we have to check both the possibilities. I mean, for discrete as well as the continuous.
Sorry, what?
For the mixed
What
random
do-
variable,
Yeah.
all the time we have to check both the possibilities. I mean, for the discrete as well as the continuous.
Yes, we have to check the outcomes of both these random variables. I mean, discrete, we have to decide what are the outcomes, and continuous, we need to decide what are the outcomes.
Okay.
And we need to plot it on the same real axis.
Okay. Okay. Ma'am. Thank you.
Uh, okay, so we discussed about how we started discussing about how to study the behavior of random variables, right? So how to study the behavior of random variables, we started talking about. So in order to study the random variables, we need to know the distribution function. We need to know the distribution function of the random variables. We need to know the distribution function of the random variables. Okay, so distribution function of the random variables we need to know. So the distribution functions, right? The distribution functions of the random variables uh, we discussed under mainly two categories, right? Under discrete random variables, right? Under discrete random variables, we have specific distribution functions, and under continuous random variables, we have another set of distribution functions, or it is defined as the probability density functions. So the discrete random variables, right? Discrete random variables are having, I mean, probability distribution functions, and those probability distribution functions we call as probability mass functions. Probability mass functions, right? So using this probability mass function, you can find the probability of the values, I mean, probability of the discrete random variable values, right? So we use a probability mass function to do that. So under discrete random variables, we have something called the probability mass function. So this probability mass function is used to find the probability of a certain discrete event happening. And then we can consider for the continuous case. And for the continuous case, we use the probability density function. We use the probability density function to define the probability of a certain event occurring. We use the probability density function to define that probability. So we discussed about the probability mass function and the probability density function in the last class. So both these probability mass function, probability density functions are known as distribution functions, right? Known as distribution functions. The name distribution is given for both discrete and continuous random variables, right? So basically for discrete random variables, we use the probability mass function. And for continuous random variables, we use the probability density function to study the behavior of the random variable, right? So as I said before, there's another random variable, the mixed random variable, right? So mixed random variable. For mixed random variable, we have a mix of both these probability mass function and probability density function. We have a mix of the probability mass function and probability density function included in its respective function, right? The combination of these two functions will be considered to construct the probability function of the probability. Actually, it will be a continuous function, because the mixed random variable contains both the continuous random variables distribution and the discrete random variables distribution. So it will be having some discontinuities at some points. It will be having a function like this. So basically, there will be some points where we have discontinuities, but basically, I mean, mixed random variable is not that not that smooth. The function is not that smooth. You have like discontinuing points. The function is at some points like having like fixed values, and then you will have a continuous value. So the probability function for this random variable will be defined using both the probability density function and the probability mass function. So the mixed random variable is therefore combination of these discrete and continuous random variables. So I think that's sufficient for the mixed random variables for the time. And then so how can we obtain the probability of a certain event occurring using these functions, right? So how to obtain the probability, right? How to obtain the probability of an outcome, right? How to obtain the probability of an outcome using these functions, right? How can we find the probabilities, right? So what we want to know is like first we need to consider the whatever the function, right? If it is probability mass function, it is a mass function, it's easy for us, right? We have we have in the probability mass function, we have the plot. We have the plot, and we can call it as maybe PMX. The function we will call as PMX, and then the random variable is like this. And since it is discrete random variable, we will have like discrete outcomes. We will have discrete outcomes like 1, 2, 3, 4, 5. For each outcome, we will have some kind of a probability like 0.6. Then this will have 0.2, likewise. So in this
We can't hear you.
lost the sound. I had a call, and I will re-explain what I was explaining, I think. So in the probability mass function, it is very easy to find the probabilities. The probability of each outcome is given from this probability mass function. So if the outcomes are 1, 2, 3, 4, 5, and each outcome, if we say 1, we have a certain probability, and that is the probability of that event occurring. And then likewise, for each outcome, the probability is directly coming from the value of the probability mass function, the amplitude of the probability mass function value. And right, so likewise we have values for each outcomes directly directly defined from this mass function. So when we move towards the continuous random variable, right, when we talk about the continuous random variable, we have to use the probability density function to find the probabilities, right? So let's talk about that next. Right, so if we have the continuous random variable, continuous one, the continuous random variable, we have to use the probability density function to find the probability of a certain event occurring. Right, we have to use the probability density function to find the probability of a certain event occurring. Right, we use this to find the probability of a certain event occurring. Right, so now probability density function we will call as PDF, right? PDF. PDF PDF is a density function, right? PDF is a density function. Therefore, we have to keep in our mind, whenever we have the density functions, we have to integrate it to find the value out of it. Always we need to integrate it, right? We have to integrate it to find the probability, right? We have to integrate it to find the probability. So the PDF function is defined using these symbols, right? Normally we give simple f and then capital letters for the random variables name, right? Random variable name, we give the capital letter. And then we have inside brackets simple x, which gives the value of the random variable. This gives the value of the random variable. And this is how we normally indicate a PDF function, right? So the PDF function needs to be integrated over a certain duration to find the probability of that certain event occurring, right? So let's say we have plot, right? We have a plot where we have a plot like this, right? So let's say the probability density function is going like this, and it is having this is having a distribution like this. And then we will have 2 points in the outcomes, right? We will have 2 points in the outcomes, and we want to know what is the probability of getting getting an outcome between these 2 points, right? Between x1 and x2. What is the probability? Do you have any question? So in order for me to find the probability, I need to integrate between these 2 points, right? So I will take the integration between these 2 points, right? Exactly, they should be vertical. They should be vertical and crossing this plot. So between these 2 points, I want to know the probability of getting a value between x1 and x2, right? So in order to find that, I will say I have to find the integration between these 2 points, right? So once I find the integration, I can get the value of this area. And then by finding the value of this area, I can find the probability of this event occurring, right? So this function is, as we said, it is fxx. So I need to find the integration between these 2 points. So this this we can denote like the probability of the event occurring between x1 and x2, right? So we will denote it like this, right? We will denote it like this, and we can put the equal signs as we prefer, right? We can take the probability of the outcome between x1 and x2. It can be equal to x2 and not equal to x1, but bigger than or higher than x1, right? So once we take this in this form, it is easy for us to find the value for this probability. I will explain that in a little while. The reason is, like, we have the equal sign in here. We need to take an additional value from the distribution functions, and specifically the cumulative distribution function, right? So when we are finding the values for this probability, we take the help of the cumulative function as well, right? So once we take the cumulative function for this probability distribution or probability density function can be found, and then we need to take the subtraction between the 2 points that we are considering. Okay, so I will discuss using the graph that is related to that. So let's say, like, I will try to draw the cumulative function. I don't know whether the space is sufficient for me here, but I will try to erase. Sorry. No. This. No. This is, so I want to, okay, I will try to redraw this, and I will draw both the cumulative function and the probability density function. So let's say it's like this, and the corresponding cumulative function. So this is the probability density function with the simple f. With the capital F, we denote the cumulative function, right? With the cumulative function, we take the addition or the sum of probabilities up to a certain point. If we take x1, x2, in here we have x1, x2. So once we take these two values, we have the some kind of probability in here, right? But I mean, that probability we cannot find by taking this point exactly. This whatever the value we have here does not give the probability of this point of having x1. Okay, so that we need to keep in our mind, right? This is a density function. The value of the density function will only come from integration. We have to integrate, and only through integration we can find the exact value of that specific event occurring, right? If we want to find the event occurring under x1, right, then we need to take the integration around that point, and then we can find the probability. So the cumulative function, what it does is it takes the probability of that certain event occurring, and then it takes the sum of all those probabilities up to the x1 outcome. So it will be a sum of integration. It will go from 0 to 1. Basically, it will go from 0 to 1. So if we have the like this distribution function in the negative region also, there's a point where we have the area is 0, right? Where the area under the curve is 0, right? We need to consider the point where we have the area under the curve is 0. We have to start from the 0 point, and then we will go, and we will, keep adding the probabilities that we obtain for each random variable of that comes as outcomes from this experiment, and then we keep adding the probabilities, and we keep on adding the probabilities, and then we finally reach the value 1, right? So the probabilities, the addition of all the probabilities of all the outcomes from this experiment should be equal to 1, right? It comes from the probability theory, right? The probability, addition of probabilities of all the outcomes of that experiment should be equal to 1. So until the last outcome, this addition will happen, and once all the probabilities are added, the value will be equal to 1. So that is the behavior of the cumulative function. So if I want to find the probability of a certain event occurring between these two outcomes, right, x1 and x2, I can find it using the cumulative functions support. So basically, we define this probability that the outcome is outcome of a certain experiment is between x1 and x2. Then the probability I can define using probability density function, and I will explain it. Okay. Right. So I want to find the probability of the outcomes staying between these two values, and then what the outcome outcome can be modeled as the integration between x1 and x2 over the dx variable, right? So rather than finding this integration, we can quickly find it using the cumulative function if we have the cumulative function values. So the cumulative function values we can define as fx2 minus fx1. That means the total probability that the cumulative function has up to x2 point minus the total probability the cumulative function has up to x1 point gives the probability between these 2 points. So the value of the cumulative function that we find respective to this x2 needs to be subtracted with this point in order to find the probability between these two outcomes. Probability having an outcome between these 2 points, right? Between these two outcomes, the probability of getting a value we can find using this area. So what we need to do is we just need to subtract these two values that we have in the cumulative distribution function. In here, we don't find the integration. We just find the values, the corresponding values of these 2 points. Let's say it's 0.7, and let's say this is 0.2. So we take the subtraction between these 2 points, and then we can define the probability as some kind of a value, right? So as I said, like in here, we don't put the equal sign because once I take the subtraction between fx2, this is the fx2 point, right? And this is the fx1 point. Once I take the subtraction, I subtract the point where x equals x1, right? If x equals x1 point, I subtract. Once I subtract these 2 points, then I subtract the probability of x equals x1 from that once I take the subtraction. So because of that, the probability of x equals x1 is not included in this outcome, in this result. So if I want to take this additional thing, I need to add it into this integral. I need to add it separately manually. I mean, by finding the probability separately, I need to add it. So from cumulative distribution function, I cannot find the exact x equals x1 value, the probability related to x equals x1 value, but that can be found using this probability density function. Anyway, like this is basically the probability between x1 and x2, and it can be found using the cumulative distribution function support, and we can define it mathematically using the probability density function. Apart from that, we also need to know some other properties related to the probability density function, which I will now discuss about. So the probability distribution, probability density function, fxx, it is, let's say if it is like this, and then I want to find a probability at a certain point. As I said before, I cannot find the value of this point exactly from this y-axis. I cannot say the probability of getting x equals x1 outcome from that certain random experiment or random event. Is this, I can't say it's 0.6 or 0.7. I can't directly read from this distribution function, right? The probability that that we get in this instance, the probability of x equals x1 is actually 0. This is always the case when x is a continuous random variable. When x is a continuous random variable, the probability of x equals x1 is exactly 0. Only if I find the integration around a region around this x equals x1 only, I can find the probability of that event occurring. Right? So this is something I wanted you to understand. So therefore, always probability density functions. If there are any density function, you need to integrate it in order to find a useful value, useful information. You have to integrate it to find the useful information out of it. So in the last class, I think we discussed up to that point, and I hope it is okay for the LJMU students as well up to this point. These are, I hope, something that you learned in the undergrad level when you came across modules such as probability and random variables and random signals. So I don't know about randomness, but maybe you have learned about probability density functions and about signals. So basically, once you are studying about those modules, you must have come across these terms that we discussed. So in today's class, we'll be discussing mainly about the different random variables that are commonly used. And one of the most popular random variable is the Gaussian random variable. Right? So the Gaussian random variable is one of the most popular random variable. Right? Gaussian random variable, right? So this is a random variable which is used frequently to model, to understand the behavior of random signals that are present in the real world, right? So used to model random signals in the world, random signals. I mean, however, like we have to make sure that we have to also keep in our mind that only selected random signals can be can be modeled using Gaussian random variables. not all the random variables in the world can be modeled using Gaussian random variables, right? It's like that. So only selected random variables are following the Gaussian random variables, but there's another important thing, right? That is like the sum of independent random variables. There's a theory or a accepted fact that the sum of independent random variables follow a Gaussian distribution, right? Right? Sum of independent random variables follow a Gaussian distribution. Okay. So the independent random variables can have different distributions. They can have different distributions. These can have different distributions. These independent random variables. Okay, they can follow different random variable distributions. But once you take the sum of all those different random variable distributions, it is said that it is following a Gaussian distribution, right? So this fact is useful. This is useful when we are modeling or when we are studying random processes with multiple different random variables, right? When we are studying different random processes with multiple random variables. We have multiple random variables, right? And multiple random variable based processes are there, right? So when we are studying those, we have to assume that the sum of these random variables distribution follow a Gaussian distribution, right? So that is useful for us to model the final distribution of the total process. Okay. So we'll be talking about multiple random variables in a little while. In a later instance. And we will talk about how we can model the Gaussian random variable now. Right? Gaussian random variable, we can mathematically model using the basic equation, right? I will first draw the Gaussian random variable. So most of the time we can say it is, I will try to draw this line vertically, right? So yeah, we will have the x here, fx, x here, right? And then we have the mean value around the mean. This distribution for density function is around the mean. So the mean value we will denote as mu, and it is the value around which the Gaussian function is symmetric, right? So around the mean, it is symmetric around the mean. And then we define the width of the distribution we define this width using the variance of the distribution. So the variance of the distribution we can find using the mu value, and the I will explain with the moments of the random variable. We will define these things mathematically as well. I think in the last class we discussed this variance and mean as well. So basically variance is defined as uh, the sub difference between the random variables square minus the mu squared. Right. So we will get into it again today when we are discussing about it. Anyway, apart from all that, we also define the Gaussian random variable using this function 1 over 2 phi sigma squared square root and e to the power. We have x minus mu, right? And then 2 sigma squared, right? 2 sigma squared. Then we have a squared here as well, right? We have the square here and sigma squared here. And this x value can be any real value in the real axis. The real value means integer and basically the floating points. Any value, basically, I mean that we can count, we can name as the real values. Then the x is a real value. So basically, this is the function that we define as the Gaussian density function, Gaussian distribution function. Right? So it is defined using these parameters mu and the sigma. Sigma and mu define the Gaussian function, the Gaussian distribution function. So that is basically regarding the Gaussian random variable. And then there are many other random variables also that are used widely. And if you want to know about any of the random variables, you can also visit the Wikipedia and you can find out the PDF of that variable, right? The PDF, CDF, those ones you can find from the sources, right? PDF, CDF, those values can be found from those sources. And finding these PDF, CDF is super important when we are trying to predict something happening, right? So most of our research works, when we are doing some research work, so any kind of study or research, we want to find out a probability of certain event occurring, right? If we want to find a probability of a certain event occurring, let's say it's x equals x1, we want to find the function that the event is following. And then once we know that event is following the outcomes of that event is following this function, then I can find what is the probability of a certain event occurring using this function, right? If I have time, I will explain to you how I have used these kind of distributions in my master thesis, if possible, if I have time. And so basically, regarding Gaussian random variable, we also need to know other factors. So I will get into it in a little while. So before moving further, I will also just write the probability definition for the Gaussian random variable between, let's say, two different values, x1 and x2. The probability of an outcome staying between x1 and x2 will be basically the integration between these two values, between x1 and x2. Right? So we know the, integration of, we know the function of the PDF, and then we can integrate it over the duration, and I can take the integration value, right? So this will give this integration will give the probability value directly. So I will let you have a 5-minute break, and after that we will continue. Do you have any questions?
Can you
Yeah.
share the screen? I couldn't
Yes.
write all the things.
Sorry.
That's fine. That E minus component is as a power or it's a multiplication?
It's a power.
Power to the entire may.
E. Yeah. E to the power minus
Okay.
x minus mu squared over 2 sigma squared. All this component comes as a power. This
Power.
entire section.
Picture?
Yes.
Could you kindly differentiate in terms of learning outcomes and content, in between the local and LGM from LGMU? So I would like to know what assignments are ahead and what kind of internal learning outcomes that we have to follow.
The module outline you are asking, right?
Yes,
The
kind of
module.
lecture plan and
Yeah. I will upload the module outlines. I have already uploaded the module outline of the ECE in our web page. So I will basically explain, if I'm going to explain about the ECE module outline, because that is what I'm very familiar with the LGMU outline. I need some time. I will share with you the PDF and I will explain to you in detail regarding that. Just give me some time. Okay.
all right, got it. Thank you.
Thank you. So is it okay if I share this screen to another screen? Have you finished this page? So about the module outline, so I will explain to you about basically regarding the differences. So in ECE, we have these contents to cover. We have a discrete time random processor, so about random processors first, and then about spectrum estimations, and about filtering, and then about wavelets and related theories. So in the LGMU one, this is the module outline, and right, the module outline contains these components. So currently actually now the module outline starts with these DSP systems, the fundamentals, the Fourier transforms, and the Z transforms, Laplace transforms likewise, and filters. So the Fourier transform, Laplace transforms, they will be done later. Okay, currently we are doing this part about stochastic signal processing, random processor spectrum, power spectral density, white noise, right? And then when we are progressing, we will be discussing about the these Z transforms, Laplace transforms, most probably in the next month, right? And then about digital filters, I will be covering that part, the FIR, IIR filters, about which we have in both ECE and the LGMU. And so, I mean, all these content are there in the ECE as well, but in the ECE, we have basically some additional features, I think, related to spectrum estimation. So these additional components, the LGMU students will also learn as additional. We have, I think, additional hours for the ECE. So therefore, I think it would be okay for you to learn these components. However, when we are preparing the exam, we will be preparing the exam based on the module outline content. So if the module outline does not have that section will not be included in your exam. I hope it is clear to you. Do you have any questions?
So is there any electronic and communication program offered by LJMS also?
It is having this same module like advanced signal processing module.
For
So
the
we are doing it simultaneously for LGMU.
masters in communication, I think, right?
Masters in wireless comm and embedded systems.
Okay.
Yeah. So is the module outline okay for you for basically LGMU students? Basically, you will follow the same lectures, and we will notify like what are the sections that you won't have in the exam, basically. So basically, some parts will not be there for you because your module contains, I think, a lesser component. I think and there are some parts that we won't be covering in the LJMU. And those parts you don't have to, prepare for the exam.
So
Is
is
that
this
okay?
So is this going to be like 100% exams, or are there going to be any simulations or assignment content?
We are actually going to be giving about, I will discuss about now, I will explain. So we have some lab assignments that I'm giving you based on Matlab simulations. So about 5 lab assignments I will give using Matlab. So I will give us lab assignments, and there will be some assignments, no, just basically lab assignments that will be based on Matlab. And there will be some mid exam. There will be a mid exam, and that will be done after about 8 weeks. After about 8 weeks of lectures, and then we will have the end exam. Those are the assessment criteria.
So we will be having 2 exams, right?
Yeah, mid exam and the end exam, basically.
What if
The lab
we
assignment.
couldn't achieve the pass mark? Will be able to repeat the exam or with the same batch?
Mid exam or end exam? End exam, right?
Yeah, for both exams.
So for mid exam, it's actually it is done during the lecture time. So it is known as again, it's not a it is not a like what do you call, like, it is like known as like a continuous assessment sort of a thing. So mid exam, of course, you don't have to repeat. End exam, if you have less marks, you can repeat. You can repeat the exam in a maybe in the next semester that it is delivered. So end exam only you have to repeat. Mid exam is actually done during the class, so it is like a sort of assignment as well. So is it clear to you? I don't know.
Yeah, I just ask things can
Okay.
happen.
Yeah, and the lab assignment, like, it is group activity,
Okay.
and this one you can get into groups of 2 people, or else you can do individually as well if you
Okay.
want. Can do individually as well, or else you can get into groups of 2 people maximum, and you can do the assignments.
For the lab variables, lab assignments, we have to come to the premises, right?
No, for that you can do at home with Matlab,
Okay.
Matlab software. So
Okay.
you can do it and submit the report, and that is it for the assignments. So
Thank you.
yeah, basically about 5 assignments I'm hoping to give.
Sure.
Okay,
Is this me?
thank you. Yes.
Thank
So
you.
all right. So again, I'm from the Jimmy batch. So
Yes.
are there assignments? So I mean, I think it's fine for the labs, but at the end exams and stuff, are the assignments for or are the exams for the 2 batches going to be the same, or are we going to have a different structure? If in that case, if that's the case, can we have like an additional revision session, especially targeted for our LJMU content, since I think there will be some changes.
As I said before, like, there are some reductions in the LJMU module outline.
Yeah,
Not much of like additions or something. So because of that, what we do is that we will inform you from these sections. You won't get questions, right?
Okay.
Basically. And then, as you said, if you want some tutorials, we will do it beforehand the weeks, but it will be most probably done for both the batches, like ECE and LJMU in the same time. But then, like, like from that section, you are not going to get some question. So for that, you don't have to worry about. It's an additional knowledge that you might get, and it's like something additional for you. Likewise, it will go on.
Okay, I've got one more question. Yesterday's in yesterday's lecture, Mr. Priyashant also asked us to ask this question for you as well. So it's been some time since we joined the LGMU program, but we still have not received our LGMU account. So we don't really have that Matlab license for online access. Is there a way that you can ask the management to provide us with our LGMU accounts as soon as possible?
Okay, so I will do that. I will do from my end what I can do. I'm actually also kind of new to this, LGMU thing, because LGMU was done by, like other, senior members. So directly, what I would suggest you to do is that, from my end, I will ask about the account creation. What you can do apart from that is that you can email to the registrar that you were communicating with, and also the program lead, maybe Dr. Sampath, and you can ask how you can get access to these accounts. And then from that, how you can get access to Matlab. And if it all fails, you can download from the, I don't know, the links, Matlab installation links that we have provided you. I think you have those links with you, right? I don't know. In the last class, I think I shared with the other students the Matlab installation link that I was able to find from the website internet, but I don't know whether it is working appropriately. So for the moment, until you get the Matlab from that account, you can use the links that are available. I'm giving the link in the chat. You can try that. If you fail to do that, you can download the MATLAB 15 version. And even in that, you have some functions and features. Hopefully it will work for the moment. Try to get a better version of MATLAB to do the coding. So actually, you need, I think, at least maybe something above 2015, I think. But the baseline is 2015 at the moment. So I will ask you a question from my end. And if you can, you just send me an email requesting that again so that I can directly let you know the response that I got.
All right, that would be better. Thank you, Dad.
Thank you. So moving forward, the Gaussian functions. Regarding the Gaussian functions, we have several things that we can define in order to find the values of the integrations, right? As I said before, the Gaussian random variable or the Gaussian distribution function is a density function, right? It is a density function. And we define it as density function, right? This is a density function. So we want to find the integration to find the value of this. We have to find the integration over certain region to find the value of the probability, right? Value of probability of a certain event occurring, right? So in mathematics, we have now if I take the probability density function like this, right? We draw it like this. So let's assume this is the Gaussian distribution function, right? This is the Gaussian distribution function, and we want to find the value of the integration between certain points, right? Let's say I want to find the probability above this outcome beta. Then there are tables available, like Q function tables available to find the Q function values of this integration, right? So this integration that we do beyond this constant value beta, right? Beyond this constant value beta is known as Q beta, and Q beta is defined as the probability of the random variable being above the beta value, and it is defined as this integration where we have the integration from beta value up to infinity, right? We have the integration from beta value up to infinity, and then we have the this function, right? 1 over square root 25 e to the minus x squared over 2, right? And then dx. Okay. So if I want to find the probability of the outcome of any outcome being above a certain value beta, then I can use this integration to find that value, right? So why have we missed some of the things in here? So in here, in the Gaussian distribution function, we had some other parameters. We had mu, we had sigma. So mu and sigma values in this case, right? In this Q function, the mu, so we consider a
Q function?
Gaussian distribution with, sorry?
What is mean by Q function? It I didn't.
Yeah, the Q function is like a standard, function, standard function where we can use a table. Like, there are some tables, Q function, Q value tables, right? So we can use this Q function and we can find from the table, like beta value, we can find from that table the value of the integration. So Q value of that beta value will give some kind of a value like 0.8 or something like that. So that table can be used. It's a standard like a table, right? So Q function values are there in the table. So anyway, now before using the table, the Q function itself means this equation basically. Sorry, this integration, right? This integration, right? This integration is what we use to define the Q functions. What we do using the Q function is this integration. Integration from beta to infinity, 1 over square root 2 phi, and e to the minus x squared over 2, and dx, where x is the random variable, right? And in here, right, in order to use this function, the random variable should follow some properties, right? The mean value of the random variable should be, right? If I take the random variable like this, the mean value of this random variable should be 0 and the variance must be 1. Only for those kind of random variables, we can use this Q function to find the value of the random variable, right? Is it okay for you?
Yeah, got it.
Mm.
Thank you.
So yeah, we can find the Q values only if the random variables follows these distributions. I mean, the mean value should be 0 and the variance value must be 1. Then only we can use the Q function. So basically, this is a standard equation that we can use in that instance. If in that instance, we can use this integration to find the Q value. So the Q value can be found by integrating, like according to this integration. By using this integration, we can find the Q value, right? So basically regarding that, uh, that is regarding, basically that's all regarding the Q function. Apart from that, we have, I mean, there are additional things you can learn about this. You can go to maybe Wikipedia and learn more about the different situations of the Q function, right? For example, like when the beta value is very large, when beta value is a very large value, then the Q function can be approximated to just this integration value. I mean, I will explain. If the beta value is very large, beta is very large, then the Q beta is going to be equal directly to 1 over 2 pi beta square root and e to the minus beta squared over 2. So, right, this is the equation if the beta value is very large. So there are equations like this, right? So anyway, right, we can use this for different applications. Let's see what are the applications where we can use. And I mean, based on the application, we need to use the specific mathematical model. So we will discuss through some examples in the later instances, like where we can use these kind of concepts, right? So based on the question that is asked, you need to select the best, mathematical model to use, right? So so I said about integration. So earlier we learned about this tail probability, right? The tail probability, right? If I am going to explain about the Q function again, so basically the Q function gives the probability of the tail or the tail of the distribution function. It is always like giving some a probability under the tail of the distribution. Probability that we can find, probability we can find using under the tail of the distribution, right? So there are tails to the distribution function. So if we have any kind of a distribution function, we can call the areas with less probability as tails, right? So if we have the maybe mean value in the very center, the mean value, if we take it as 0, and then if we have the Gaussian distribution function, which is a symmetric one, then we can define that the tail values can be around this area where the probability of these events happening are very low, right? So we call this the tails, right? Tail we call. So to find the tail probability, we use basically the Q function, right? And so secondly, right? Secondly, we use the error functions or complementary error functions to find the probability of an event occurring between two variables, right? If we have like the Gaussian distribution, and if we have the mean value in the middle, right? If we have the mean value, we have the mean value in somewhere in the middle. We have the middle, so in the middle, let's assume this is the middle, right? So if we have some kind of if you want to do some kind of integration in between two values, that is in between these two like points, right? Let's say I want to find the integration between these 2 points, then I have to use another function, which we call as the complementary error function, or we call it ERFC function. ERFC function can be used to find the probability between 2 points, probability between 2 points, between two outcomes, right? Two outcomes, right? Probability between two outcomes, x1 and x2, right? So this error function can be used. So error function is also defined for a specific Gaussian distribution, right? I said that earlier, the Q function is defined for a specific Gaussian function, right? The Q function was defined for mu equals 0 and variance equals 1. The complementary error function is defined for mu equals 0 and variance equal half, right? So those are the slight differences. Mu is equal in both instances in Q function and error function, but the variance is half in the error function, right? So what we do using this complementary error function is we try to integrate this Gaussian distribution over this range, right? So you will ask, like, how can we use these functions for any variance and any mean that we want, right? If we have different variance, different mean values, how can we use this complementary error function, right? In that case, we need to do some manipulations in our integration to get the necessary mean value and the variance effect into that, right? So I will explain about the error function again in the next slide. So I will draw this same figure that I have drawn secondly. So I will erase this slide, right? The error function, ERFC, I call this error function is defined to model or give the value of the integration between two outcomes of the random experiment. It's x1 and x2, right? Between, if I want to find the value of the probability of certain event occurring between the outcomes x1 and x2, then I can define it as now, since I'm taking this Gaussian distribution, right? I'm taking the Gaussian distribution, right? I'm taking the Gaussian distribution, so I have to draw a vertical line. So, so I will. So let's assume it is a vertical line. Mu equals 0 here. So x1, x2 points, let's say they are same for the moment, right? x1 and x2 can be any values, but let's say they are same, right? But so in the standard function, we are trying to find the probability between these 2 points where these are equal and opposite, minus beta and plus beta, or minus gamma and plus gamma. So I will erase x1 and x2. I will put gamma here and minus gamma here, right? So this is the case that this error function is defined for. So when we want to find the probability between these two symmetric points, and that is defined, right? That is defined ERFC, right? ERFC, or complementary error function. Complementary error function is defined as the 1 minus integration between minus gamma to plus gamma, right? These are the gammas, right? Minus gamma to plus gamma. And you take the integration of 1 over square root pi e to the minus x squared into dx. Okay, so in this case now, when we take this integration, we have considered a situation where the mu value, we have considered the distribution where the mu value is 0 and the variance value is 1 over 2, right? So when we substitute mu equals 0 and sigma squared equals 1 over 2 to the original Gaussian distribution, we can get this integration part, right? The range, of course, varies. The range is from minus gamma to plus gamma, right? So basically, this is the definition of the ERFC. So if I want to find the integration between these 2 points, gamma, minus gamma and plus gamma, then I want to use this integration, right? So I hope it is okay for you. Apart from that, now this function we can further define as the further define as 2 into gamma up to infinity, this same integration. The reason being the sections around the distribution around this mean value is similar, right? So if I take the summation, if I take the subtraction from 1 and I subtract the tail areas, then I can take the remaining area, or this shaded region, right? This shaded region is twice the integration between yeah. So sorry, I think I have to explain to you again this concept. Okay, so actually this shaded region is ERF function. So it is the error function region. Okay, error function region. However, from the ERFC, we are finding the complementary of that error function region, which means we are finding the rest of the area, this area, not the middle one. Okay. So
What
sorry.
is the practicality of this error function? The error region means the real thing about the error region.
The real thing means like we are trying to find the integration of this integration under this distribution function. So integration will give the probability of that certain event occurring.
Oh, okay.
So there's no like error function. That the meaning of that title is not that related to the real world, as in like I don't know really what is the reason for the title, for putting the title, but the error function is basically finding the integration under this distribution function. Right? So error function region finds the integration under these certain random variable values. So like error function, error function, if I say ERF, if it is the error function, then I will be finding the integration between two specific points that I define, and I take the integration under that point, under those values, using the integration that is defined in the standard manner. So if I want to explain again, the integration is this one. The integration that we take between minus gamma to plus gamma, and integrating over this distribution function. This function will give the area under the points, minus gamma and plus gamma random variables, right? So this integration will give that value. So the reason for using, for defining the error function, as you asked, like for example, if I want to explain about the usage of this function, in Matlab, for example, we can directly get this function. And in other, other maybe softwares or other tools like Python, or when we are using Java, we define this function mathematically. What we need to do is give the region, or give the region of the random variable values. Once I give the region, then it will calculate the error function value basically for me. So the integration is a standard integration that is defined in many statistical applications, or many statistical, like in many places this is used, ERFC. So we directly use this function as a maybe function that is used in Matlab or Python tools. Then we can find the value of this ERFC very easily. That is why we are using this. We are trying to study this. So basically, this is the integration that defines that function. So this is the ERF function. ERFC function with the C is 1 minus of that ERF function. So 1 minus ERF function means it gives the ERFC gives the area under the curve that is apart from the area that is in between these two values. So all the rest of the areas that are apart from the middle area will fall for the ERFC value. If I find the ERFC value of gamma, it will give the area under the curve, which is above gamma region, and below minus gamma region. So the sum of these two areas will be given from this ERFC function, right? And that ERFC function can be used for many applications, right? When I'm like for in the real world, right? If I want to find a situation where I get the outcomes of the experiments above and below these gamma values, right? If I want to say that I want to find the situation where the probability of this outcome happening is above this value, right? Gamma, right? So if I again explain this tail, in this distribution function, we call this a tail, right? So in tail, we have the probability is very low. I mean, we can see that the probability of the events occurring is very low, right? Now, this is the probability density function. So this probability density function gives us the probability of some kind of event occurring. So when you take the events under these points, like that are above gamma, I can see probability of these events happening is very low when compared to the probability of events happening between this minus gamma and plus gamma, right? Do you agree? Right? So the probability of these events occurring is very low, right? However, like in situations like in the real world, we want to see these kind of events, like what is the probability of these kind of events happening? What is the probability of some event happening, which is kind of very rare events. So this area gives the probability of a rare event occurring, right? A very rare event occurring. Okay. And it is very useful for us when we are trying to propose some kind of a solution or propose some kind of algorithm that works under every situation, right? We are always trying to propose algorithms and solutions, right? That should work under most of the situations, right? And it should work under critical situations or rare situations as well, right? So we need to therefore find out what is the probability of this critical rare event occurring. And in that situation, we can find the probability of this tail. Right? If we can tell that, okay, tail probability is really low, then I can say the probability of this rare event happening is really low, and I don't have to really address that problem. But if the rare event happening is kind of considerable above a certain threshold that is defined in the world, then I need to consider the probability of that happening as well, right? And based on that rare event occurring, I need to provide a solution that can address both the rare event and also the normal events happening, right? I hope it is kind of clear to you. And this tail is really important, therefore. And it is something that a lot of people are researching about still. And they have to find solutions to these rare events occurring, right? So these are unexpected rare events. Okay, I hope it is okay to you. The tail is about unexpected rare events occurring. So if I want to find the probability of this tail event occurring, I will use the error function or ERFC. And ERFC is defined as 1 minus this integration, right? And if I want to simplify it further, I can say it is 2 times the gamma into up to infinity. And I will continue this integration as usual. All right. So it is 2 times because of the symmetry. It is coming because of the symmetry, right? Symmetry around the mean value, right? I hope it is okay for you. And if you don't understand, you can let me know. And if even then you don't understand, I hope you can revisit these theories again. Then you can let me know in the next class or something. And you can try to find on your own as well, like how these models come and what are the like understanding behind these models, right? So I will just stop at that point. I know it is a lot of maths. So I will stop at that point and you can refer related to these concepts in your free time as well. So as I said before, we have to know about all these events occurring in the world, in the random events, and we need to know the probability of these random events occurring, right? So I will erase this slide if it is okay with you. And we talked about the Gaussian random variables earlier, right? We started and we talked about the Gaussian random variable basically as of now. We defined its like mathematical model, right? It's mathematical model. I mean, it's a PDF, right? We defined the PDF, and then we defined basically ways to find the values of the Gaussian random variables using Q function and using the ERFC function. Using this Q function, ERFC functions, I can find the integration of the Gaussian random variables between specific random variable values. So Gaussian random variable is one of the most popular random variables, but it is not the only random variable that is available. So there are other popular random variables. Okay, there are other popular random variables that are in existence. So we have uniform random variable. We have the gamma random variable. We have the Weibull random variable. So in my master thesis, I can remember I had to use, because of the application, I used this Gaussian random variable, the uniform random variable, the Weibull random variable in my work. Even in my PhD work, I used the uniform random variable and also the Gaussian random variable mainly to model the different, application centric modeling and in order to model the maybe the location of the devices, the location of people, I can use random variables. Then I also use the Rayleigh random variable, to model the channel coefficients in wireless communication networks. So these random variables can be used to define how the how the values of the channel coefficients vary in the real world. So random variables are used to kind of fit the signals with the mathematical models. So we are trying to find a mathematical model that will be very similar to the actual random signal. Yeah, so we have to search about the in order. So you have asked a question, how to find the best fitting random variable. It's a very good question, right? We have to search about the random variables behavior, right? So as I said before, I have in my master thesis, I have used multiple random variables, and I think I will explain to you maybe as I remember, right? This is my master thesis presentation. So basically in my initial modeling, I assumed that the measurement error in the distance estimation will be following a Gaussian distribution, right? So this is a accepted fact in the world. Measurement errors of sensors follow a Gaussian distribution. So based on that fact and from the literature, I find like what is the distribution that very much fits this error And then I assume that measurement error follows a Gaussian distribution, right? And based on that, I estimate the error that can occur at different error levels. What is the probability of that error level happening, right? So this is one instance. And then I used another distribution function, basically the Weibull distribution function, to model the lifetime of the sensors. The sensor failure lifetime. At what time the sensor will fail. So the probability of a sensor failing at a certain time I can find using the Weibull distribution. So not only Weibull distribution, I need to combine it with different components of the Weibull distribution or different variations of the Weibull distribution to find the best curve that can predict the failure time of a sensor. All right. So I used a curve called bathtub curve. So this curve looks like a bathtub. So I use that to predict the time that it takes for the probability that it takes for a sensor to fail at a certain time. Okay. So using the probability, I define, okay, whether this sensor is going to fail in the next second or not, or in the next minute or not. Based on that, I make the optimization in my model. Right, I define the probabilities using these functions, right? And then I find the probability of something happening, right? Something that happening in the future. And likewise, I based on that, I try to find the probability of the error or sensor failing. And in order for me to obtain the efficiency in the system, I try to select sensors, new sensors, if there are sensors that are going to fail in the next minute. So this optimization algorithm was used to select the best sensors and replace the current sensors. So likewise, we can use random variables to find the probability of, random events happening. So we can use these distributions that are already defined in the world to model our random signal. So we can define measurement errors using Gaussian random variables. We can define noise using Gaussian random variables. And as I said before, other parameters such as height or distance, kind of positive random variables, I can define using gamma distribution. Gamma is a fully positive distribution, and it is having values it is having probability values for random variables which are above 0 only, right? So above 0, and the probabilities of those events occurring we can find using this gamma distribution. Weibull distribution is also a positive only distribution, and it is also used for variables such as I said before, sensor failures and likewise, right? So these are some practical applications of these random variables. So really random variable, as I said, it is widely used in wireless communication and other applications as well. So there are such kind of random variables. So I think I saw some questions. I have, yeah, I will be sharing the recording in the LMS. I don't know whether you have access to the web page that I'm sharing it with. If you're not having the access, then I will share the recording in your own, module page, and I will share the reference books in that page as well. So I have uploaded already the module outline in the LMS for the ECE students. For the LJMU students, I will upload the module outline there. Right? In the LMS, if possible, go and check. In the ECE, I have already uploaded the module outline. I have uploaded the reference books. You can have a look at that. Right? The reference books I have provided are these ones, basically. And the module outline is uploaded here. And I have asked you to join a group chat in this link. So you can ask any questions you have regarding the module using this by joining this space. So for the new students, you can join through this link to that chat. So the video recordings I will upload in here. Right. Right. So we learned about different random variables. We learned about what random variables were. So we learned a lot about random variables. We learned about different types of random variables. And now we are going to further learn about the characteristics of random variables using the PDF, right? We learned about the PDF earlier. And we are going to further study about this PDF now. Right? We are going to further study about this PDF using some mathematical definitions, right? So we want to further study this so that we can find like statistics, further statistics from this PDF function. So the PDF function, it could be something like this. Let's say, yeah. So I will draw it in a way like this, right? Like this, right? So the probability of I will right the probability of this distribution, probability density function of this distribution is like this function, like this curve. So the probability of some events happening are very less. So that this probability is kind of less after this area, right? Beta or something. The probability of this event occurring above this beta value is kind of less. And then when you consider this side, it is kind of higher than this right side. So kind of higher, but not that much, but it has some probability better than the or higher than the right hand side. Anyway, we have, as we discussed earlier, we have these parameters that we use to study this probability density function. So the main parameter, the first parameter is known as the mean, right? It is known as mean or the mu. So mean is a first order statistics. It's a first order statistic and first order statistic, right? It's a first order statistic. It represents the average value of the random variable. It represents the average value of the random variable. It gives the average value of the random variable. Then I talked about the variance, which we denote as sigma squared. It is a second order statistic. Second order statistic. Okay. This is second order statistic. And then we have two other parameters. No, I mean, when I'm talking about the variance gives me the spread of the the spread of the density function, or the width of the density function. The variance gives us the width or the spread of the density function. This gives the spread or the broadness or the spread of the PDF function, right? How broad it is, right? You can find the kind of the width of the function using the maybe, I mean, roughly you can find the width, or you can visualize the width using this function's distribution. I mean, using the figure, but mathematically you can find using the equation. The variance value you can find the using the equation, right? So spread broadness of the PDF is given and represented by the sigma squared. There are other factors or other parameters such as skewness, the skewness of the PDF, and it is the third order. It is a third order statistic, right? The third order statistic, right? This is third order statistic, and it is giving us the degree of symmetry around the mean. Degree of symmetry around the mean. This gives me the degree of symmetry around the mean. So how much of symmetry is there in around the mean, right? And then it actually gives me what is the, I mean, difference that we can see between the tails of the distribution, difference between the tails. Between the tails or the tail distribution. So in here, now the tail actually defines the symmetry of this function, right? If there are different tails, I mean, this tails area is different to, I mean, this tail. So the difference between these two tail areas will give me kind of the symmetry of the function around that mean. Okay, so the skewness is the third parameter. And then I can take as the fourth parameter the kurtosis. And it is the fourth order statistic. Fourth order statistic. Right? Fourth order statistic, right? So it is a parameter that is used to measure the size of the tail. Measure the size of the tail. Of the tail areas. It is used to measure the size of the tails, right? And it is used to represent the occurrence of rare events. Represent the occurrence of rare events. Represent the of rare events. Represent the rare event occurrence. Right? So represent the rare event occurrence. Okay. So those are basically the parameters that we can use. So as I mentioned to you, these statistics are in first order, right? The mean is of first order statistic. Variance is second order statistic. This is first order statistic, second order statistic, third order statistic, and fourth order statistic. So likewise, there are like nth order statistics that we can define for the PDF, right? Based on the different order statistic, we can get some information about the probability of the outcomes of the experiment, right? And those different statistics we can generalize, and we can say as moments of the moments, as we can say moments, and right, we can define these statistics as first order moment. This is I will write that in separate slide. So the mean value, we discussed about the mean, the variance, then about the skewness, the kurtosis, right? We discussed about all those um, parameters, right? So these parameters, this is first order, this is second order, this is third order, this is fourth order. So we likewise we can define an mth order statistic. Mth order statistic. So for the probability density function, we can define mth order statistic as well. So such kind of a mth order statistic we can define mathematically, and we will discuss about that now, right? Okay, so if I'm going to explain to you mathematically the mean function, mean can be basically represented using mu, or I can represent it as the expectation of the random variable x, right? And it can be represented using an integration that I will take between maybe two real values, and I will take the integration of this x random variable with I will take the product with the PDF function fx, x, and dx. And then the sigma, or the sigma squared, or the variance, I can write as expectation of x minus mu squared, right? I will variance is second order statistic. So variance I can write as sigma squared, and I can also write as E inside brackets capital X minus mu squared. So it gives me with respect to the mean, how the random variable X is varying and how its squared value is varying actually. Okay, so this is also known as a central moment, but we will get into that later if required, right? So this expectation value, right? Expectation value is defined using integration as uh, uh, the x minus mu, right? X minus mu fx x dx. So whatever you put inside this expectation operation, you can put as the value inside this integration. And the power is also similar in this integration. So if it is x squared, it's going to be x minus mu squared is going to be x minus mu squared in this integration. Likewise, we can define different orders of, statistics. And if I'm going to get mth order statistic, right? In general, it will be mth order statistic will be, let's say EXM. It is EXM. I can define that as the integration of XM into the PDF into the DX. So this is the mth order statistic. If you want to find any order statistic, you might need to use this expectation or E of X values. E of X or E of X squared, E of X a third you can find using this equation. So if I substitute m equals 1, I can get the mu or the mean value, right? M equals 1 will give me the ex value. M equals 2 will give me the ex squared value. M equals 3 will give me ex3 value. Likewise, you can use this equation to find any moment of the x value, right? The expectation of the x value I can find under any moment, under any 1, 2, 3, 4, likewise up to nth moment I can find using this integration. This is how it's defined basically, right? However, now variance is not the directly not the second order function. Variance, there's some difference in here. In the variance, we have some subtraction with respect to the mu. It's not directly x squared. This is not x squared, right? This is x minus mu squared. So this variance definition is a little bit different than the direct nth order definition. We will get into that. So for the moment, I think if this is actually we can discuss about only the second order. We can say, okay, the second order moment, second order moment of this variable x is going to be ex squared, and it might not be variance. This is not variance, right? This is not variance, and this we can define as x squared into fx x dx. So this is the second moment of the random variable x. The mth order of the random variable x is exm, and it is xm into fxx dx. So from that point, I think I will stop discussing about the orders or mth order statistics, right? So these are known as moments of the random variable, right? Moments of the random variable, right? So we will discuss about this in the next class when we talk about the theory. So now I will discuss about maybe 1 or 2 MATLAB simulations, and then I hope it will be something different to you. So I want to go to the MATLAB simulation. Is it visible? Okay. All right. So we will stop talking about the theory now, and now we will do some simulations, right? So we talked about, anyway, I will discuss something regarding Gaussian variables. So you know about the ECG signals, right? ECG signals that we use to measure the heart pulses of a patient or a human, right? So we measure the ECG signal using some sensors that we place around the heart. And that ECG signal is known to follow the Gaussian distribution, right? From the studies, after multiple studies, people have found it is following Gaussian distribution. So now what I'm doing in this code is that I'm trying to find the probability density function of this ECG signal. So I don't know whether you can see the code. So I will try to make the view much bigger font wise. However, I think I need to go to preferences and fonts, and there I can increase the size of the font. So why? Okay. Actually, I don't know whether it did any difference. So command editor, edit, should be edit, right? Oh, sorry. Okay. I think it's much better. I'm first calling, I'm getting a ECG signal, and then I'm going to plot the ECG signal. So I will run this program, and then I will be asked to give the ECG data. So this ECG data I can find in the internet, right, using as a data file. So as I remember, I went to a link in the website where I was able to find the ECG signal, and it was in the data file format. Okay. And then once you give that, then I use this, I sample the data. I think, yeah, I do sampling of the data, and then I normalize the data. Normalizing means that I try to bring the data within a certain range. So I mean, first I plot the original data in the figure number 1. This is what I get. This is the ECG signal with respect to the time. And the amplitude of the ECG signal strength are given at each time. And it follows this kind of a variation and this kind of a pattern. So we can see some noise is included in this signal, right? The variations are there. So there are slight variations in the signal, like there's some noise-like signal, like noise-like addition in this signal, right? So because of that, I think, I mean, basically because of these kind of noise signals, randomness is added into this ECG signal. So once we then if I want to find the probability of some kind of amplitude occurring, right? Some kind of amplitude in this ECG signal occurring, I can take the amplitude of these values, the values, the wave of the signal. I can find the mean value, average value of these signals. Whatever the signal data I obtain, I take the average value or the mean value. I can find it using mean function, and then I find the variance using the variance function. So variance mean those are already defined functions in Matlab. And then I can also draw the PDF function of this PDF of the ECG signal amplitudes or ECG signal values. And once I draw it, it looks like this. So it looks like this once I draw it. So it has an average value of around 0.7, between 0.75 and 0.8. And its variance is like not that wide, but somewhat in average. And the probabilities are like this. So the values, that outcomes values, some data that related to this outcomes are not there. So because of that, the plotting has not happened at that region. The outcomes for that amplitude has not been there. The amplitude of the ECG signal has gone from 0.7 up to about 0.95 when, right? So however, now I have normalized it. So therefore I have to multiply this amplitude by the maximum value of the maximum value I can observe in this ECG signal, right? So I use this line to normalize the signal around the maximum amplitude I was able to see. So I normalize this in order to get the signal amplitude, so the signal amplitude values into a certain range. So now by doing this division, I have get it to a value between 0 and 1, right? To a value between 0 and 1, I have got the values of the amplitudes. So I hope it is okay to you. I will share with you the codes of this if you want. Okay. So this is how the PDF of a certain random variable can be plotted in Matlab. Okay, using this function, you can measure the probability of getting an amplitude of maybe 0.85 or above using the Q function. So that's what we discussed in the theory, right? So we can obtain the PDF function. After finding the PDF function, we need to find the probability of a certain event occurring. And to find that, I have to find the integration below the curve above that certain random variable value. Then I give the error, whatever the function, Q function or error function. Then I find the integration value. Then I find the probability of that event occurring. Right. So for ECG signal processing, I might need to know what is the probability of the amplitude going above this value, right? So I need to find out if whether it is a an unhealthy thing or something critical. So I can find the probability of such kind of events occurring. Then I can maybe do some solution, give some solution. So that is one thing I wanted to share with you. Another thing is that I want to show you another example from the Matlab signal analyzer app. So I think today we will discuss about this example. So in the last class, we discussed about how we can filter signals using the signal analyzer app, right? So when we are using the signal analyzer app, we can easily process the signal. We don't need to do much of coding. Okay, so we don't need to do much of coding. We can use the functions already available in the system. So first and foremost, when you want to go to the like signal analyzer, you can type signal analyzer in the command window, or else you can select the signal analyzer app from the, you can type signal analyzer in the command window and you can get the window. Okay. Signal analyzer window you can get. So whatever the variables that we were able to obtain by running a script in the Matlab interface, I can obtain in this signal analyzer app as well. So since I ran the ECG signal based code, I have got the variables of that in this window, right? However, if I want to analyze that, I can do that also in here, right? You can see the pattern of the signal in this window, ECG signal in here. If I want to do high pass filtering or low pass filtering or band pass, I can do in here. And I can take portions of the signal to analyze. In this example, we will discuss about another signal, right? We will not discuss about this ECG signal, right? We will, if you want, you can do the ECG signal analyzing in here. I will delete it, this one for the moment, but I will just keep it just in case. And in here, I'm going to go and I'm actually going through the example that is available in the MathWorks website regarding this extracting signals or regions of signals from the whale song. So the whales emit some signals, and those signals have certain patterns. That is what we are trying to see in this simulation. So I don't know whether I have shared the sound. I will share the sound, and I will run this, and you will be able to hear the sound of the whale. So hopefully. Great. So now we are going to see the signal in the signal analyzer app. So since I run this code, these variables are stored in the signal analyzer app. So in here, I can see now whale is here, right? Whale signal is here. So I can put it up to this signals table or the area where I'm going to use the signal. And I can plot this, right? I can plot this signal in the time domain, this plot. All right, I can reduce the display, so I can put it like this. So if I want to find the frequency domain spectrum, I can select the frequency spectrum. And I can see the frequency of the wave. If I want to do high pass filtering of this signal, then I can go to the, I can first create a copy of this duplicate, right? I can create a duplicate and then I can rename it as high pass, right? High, and then I can then I can clear this display first. Then I select this display and then I select the high, the one that I'm going to do high pass filtering on. Then I go to the analyzer and go to high pass, and then I can select a frequency above which I want to do high pass filtering. And then I can select the stop band attenuation based on my requirements. I will put as 80 dB. So stop band attenuation gives me an idea about like how quickly the attenuation happens, or up to like what is the uh, what is the width of the attenuation happening in the filter. So you can also view how the stop band attenuation is defined in the standard filter definitions, right? Stop band attenuation is defined. Stop band attenuation is defined as the attenuation that we can define between these two regions in the filter design, right? So in the filter design, we give the amplitudes of the filter and how the amplitude of the filter should vary. Sorry, amplitude of the signal should vary after this frequency point, and the stop band attenuation gives this height. So we can define for our high pass filter what is the stop band attenuation. So for this example, it has been defined as 80 dB. So we are defining it likewise. So afterwards, we will run the high pass filter and we will be able to get a high pass filtered signal as the output. So once it is filtered, it will show with this symbol that it has done the high pass filtering. So in the frequency spectrum, you can see only the high pass or high frequency above the 925 frequency component are retained. Other ones are having a lower amplitude. So this is the high pass filtered signal, right? And so apart from that, now high pass filter, I mean, we are talking about the whales signal. So whale has like high frequency in its signal, and this is what the high frequency nodes are. We have filtered them. Can you hear me? Okay. apart from that, we can find the other regions of the signal, whale song's signal using the original signal. Right, so I will clear the display. Now I don't want to see the high pass filtered one. Now I want to see the entire original signal again. In this original signal, we have these three regions that is called as Mohn regions, right? So it is having a similar pattern repeating. Now this patterns like the amplitudes of this signal is repeating 1, 2, 3 times. The first one has a different pattern, but after the first one we have these Mohn sounds. And now what we are going to do is we are trying to find what this signal is. We are trying to extract it, and we are trying to get that part only and study it. So what I want to do is I have to go to the display, and I have to select panner, and then panner. In the panner, I can select the region from the region. In here we have 6 seconds, and here we have 8 seconds. So between 6 seconds and 8 seconds, we have this Mohn sound. So I will filter, or I will take only the signal component during this region from this panner. So now I can see what is the components, what is the amplitude that I can see here. And then I can also see the frequency components of this region, right? So 1, 2, 3, 4, 5, 6, 7, 8. Likewise, some frequencies like peaks are there under specific frequency components. And basically, this is what we can see as the frequency components and the amplitude of the signal component during this region, 6 seconds and 8 seconds. Then we will actually, save this as a separate signal bit. So I have to save it by going to extract signals option and selecting between time limits. So once I do that, I can see I have formed a separate sound signal in here that contains only this component from 6 to 8 seconds. Again, I go to the original one. Again, I clear the display. I don't need it because I have already created the signal components I need, and it is already here. And then in the original signal, again, I want to see this one, the second Mohn signal. So I go again to the panner. And the panner, I can select from region 11 seconds up to 14 or 13 seconds, or 11.5 up to 13.5. So I will select that region so that I capture all the different amplitudes. And then I again extract that also as a different signal, right? So it is now coming as ROI and ROI1 likewise. So in here I have the signal components saved. And then again I clear this display and I go to the original signal, original signal is whale. So in the whale I again take this component where I have all the different amplitudes, and I extract that part also. So I have taken different parts from this signal. Now I will again clear the display, and now I will plot all these Mohn signals only, right? Now in the whales signal, as I said, now these three regions are similar. So I want to see like whether they are similar actually in the frequency domain, in the time domain, and right. So to do that, I will plot these three components in the same plot, right? So what I do is I will clear the display. What I do is I will plot them all in the same plot. Now see, I can see similar amplitudes are there in all these three signals, right? And I can see the frequency component of these three signals also fall on the same, like overlap each other, right? So it means that the whale is producing the same signal 3 times, with the same amplitude, and the frequency or the power spectrum density of the frequency components, or the power of each of the frequency components, are also similar in all those 3 instances. So this is what we can observe as an output. So I can also use some data cursors to find the peaks of these signals, like 36, 37, 41. These are very similar values. The peaks values are also kind of near. So if I want to find two data points, I can go to data cursor and I can select two different points to compare. I can compare this point and a very low frequency point. I can see the values of the amplitudes of the amplitudes that I can take under certain frequency. So likewise, I can analyze and I can find about these signals. So now, do you have any questions about the simulation? So I will go back to the command window and I will run. I have already coded this. So I will run different sound components that we can obtain, right? So I think before coming to this code, you have to, after coming into this point, you have to extract these signals. You have to extract these signals, export these signals as a mat file into the command window or the Matlab window, Matlab normal workspace, right? So in here, I will put as region v3.mat, right? I want to analyze the region, so I just put it as region v3. And then once I go to the command window, I will be able to see it appearing as a data set in here, region version 3, right? So under region version 3, if I select, I can see all the signals that I have tried to obtain using my signal analysis. And then I will now run this code, right? I think I will run this part only for the initial, the original signal. And then once I want to get the data that I have got from the analyzer, I have to load that data. So since it is region version 3, I will put as region version 3 here. Then since I want to analyze the high pass component, I put that high pass component here. Then the regions, right? Region ROI1 and ROI2, I put in here, right? And then I want to do some analysis on the signal components and combine all those components and analyze them. So currently I have coded it like this. Let's see if there's an error, we will fix it. Until this point, I will run it. So in order to run it up to a certain point, I put the debugging point in here. Then I ran the code. So I think the whale sound is coming, but yeah. So at this point, I got an error called regions version 3 is not found. So I have named this as, I have named the file as region. So I will remove the S. Now from that point, I will now, again, I will now comment this one. I don't want to hear the whale sound. So I will try to only listen to the high pass filtered component. Right? Right. Some sound is running. Need to make it stop and then I will again. Okay, so I will run this. So the high pass component has a lot of high pass frequencies, I mean high frequencies. In the next signal components, you will hear it will have some low frequencies. So I in these three components, you must have heard the same sound is coming. Same sound is coming about 3 times. Mon region 1, 2, and 3. About similar sound is coming. Okay, so I hope it is clear to you. Now we discussed in this plot that all those 3 Mon regions are similar, right? Mon regions are similar, and therefore we get the same sound in all these 3 regions: Mon region 1, 2, and 3, right? So therefore we get the same amplitudes in all these Mon region 1, 2, and 3. So if I want, I can combine the different signal components, and I can hear the signal components. And if I run this one, I think I might run into some error, but we will run this. Yeah, it gives an error because it says the row index exceeds table dimensions. That means like one of the signals do not have that kind of do not have enough data. So I need to find the signal with the least amount of data, and then I have to add that same amount to all the I mean, I have to take that same amount for all the different signals. So if I want to see the signal components and the amplitudes, I can observe it using this what do you call this? Variables window. So variables window will show me what is the size of the signal. The size of the signal as it appears is 8235. And in here, the second signal, I will go here. So the 3 signals that I'm looking at have this kind of sizes. The lowest size is 7640. So I will put it as that. Right. So I will run it now. Hopefully it will get run. Yeah, it is coming. I will run it again. I think some kind of a bracket is missing. I need to replace it with the correct one. Then I will run again. Right. So the combination of all the Mon regions gave the same sound. And then I want to, right? I will then try to combine the high region and the low region, or the morning region and the trill region. Now I want to again replace. Right. I will try this. It has both the high pass and Mon region waves. Then you can do likewise. You can combine. You can do different combinations. You can do different combinations of signals, and you can listen to the final output. Likewise, you can do signal processing and changes. You can change the original signal and observe the output. So that is basically regarding the Matlab simulation I wanted to show you today. So with that, I would like to end today's session, right? And there are 15 minutes. If you have any questions, you can ask. Otherwise, you can leave the lecture. So thank you so much for participating in today. So if you have any questions, you can let me know.
Thank you, Doctor. So these M files and everything, will you be sharing these links or the relevant files? Seems that at least for now. So I'm an LGM student, so our LMS hasn't been updated yet. So I think we haven't been enrolled into the relevant modules yet. So
Yeah.
is there a way that
So do you have access to the LMS?
we do have access to the LMS, but I'm only seeing modules from our previous semester, but not
Okay.
anything from this semester.
Yeah, and I will share with you my my GitHub like repository link where I will be uploading this code. Okay, you can access it and you will be able to access the codes. Okay.
All right. Thank
So I will share it now itself so that you can we can go and have a look at it. So right. So this is the repository I have for you. So advanced signal processing lectures, and I will be able to share this with you. I will add the today's codes into here. Okay, you don't have access to LMS. You are from ECE, right, Martin? I think you're from ECE.
Yes, madam. Yes,
So,
madam. But
yeah.
previously I was access. But
You had access.
I couldn't access today. No,
You never was able to.
no. Yesterday, before yesterday I was access, but today I couldn't
Okay.
access.
Did you log in from the Google SSO or?
No, the SLTC website, LMS.
Do you have an email address from SLTC?
Yes.
Use that to log in from the Google SSO. Like from the Google sign in, you go through that and put your SLTC email and then use the password that you're using to access the maybe that account.
Likewise, only I access the email, but the LMS I couldn't access.
All right. Maybe you can try one or two more times and then you can email me if you don't have the access.
Okay, madam.
Right?
I'll try.
Thank you.
Thank you.